open by any chance? Not yet, at least. But maybe I do need this in an hour. There's ventilation, of course. But ventilation is not perfect. Okay. So, next lecture. Okay.
So the next lecture, maybe more than one lecture, is on the localization in the UKF. And so localization is a very big issue for running UKF-based data simulation systems. Because our ensemble size is so small, like rarely it exceeds 100. So we have only so few degrees of freedom. So it's, for the system to work properly, we need somehow to match the number of degrees of freedom in the physical system. We try to match, and the number of degrees of freedom in the data simulating system. So this is done typically by reducing in one way or another the spatial area where you assimilate your observations, which is called localization. This is whole approach. So if you consider running NKF with anything bigger than perhaps with any model with a state vector bigger than a few thousand elements, you will probably have to use localization. So what's the reasons for using localizations? If you consider the literature, there are two main reasons which are cited. The first one is so-called spurious covariances. If we take any ensemble and calculate covariances with this ensemble of finite size, we will see that there are some very surprising strong correlations which are very far apart, which probably cannot be physically related. And what does it mean in practice when we run this system? It means that assimilating observation at one point will also reduce the uncertainty, the ensemble spread, in this far away point. As a result, your ensemble spread reduces much stronger than it should. So this spurious covariances lead eventually to the ensemble collapse. So in the underlying reason for the occurrence of this spurious covariances is in the very core, I think, using the statistical approximation for the covariance. So this is known as the best. That's the optimal unbiased statistical estimator of covariance from given samples. And so there is actually these days a lot of research done on how well actually this works. And so this is mainly comes from the computational biology, because they use these estimations in covariance when they try to decipher the DNK. So there are lots of papers which consider this problem, and the overall conclusion is that if your system has, for example, n degrees of freedom, then to use this estimator, you have to have ensemble much bigger than n. Your ensemble size is even of order of degrees of freedom in your system. This doesn't work very well. So if, for example, we consider physical system Earth and atmosphere with the grid size typically used, how many degrees of freedom are in there? Perhaps many thousands. And it's quite unrealistic to run MKF with the size ensemble of much exceeding that. So The second reason, which is cited in the literature, is the relation between the ensemble rank and the model subspace dimension. Say if we have ensemble size m, and if we simulate in special tiles, if this is our whole domain, then effectively we increase our effective ensemble rank by the number of tiles by x, by number of tiles by y. So, say, in this case, we effectively increase the ensemble size 6 times. So, which reason is actually much more critical? We'll return to this later. But here, no, it's actually on this slide, which I already shown. And this is the performance of the system with the linear model versus the ensemble size. So let's consider the performance of this, for example, square roots system. Say if we had a problem of spurious covariances, this problem of spurious covariances in theory should exhibit itself at any ensemble size, because this approximation is statistical, right? So we should have seen this tail reduces at rate of ensemble size to the power of -1/2, while in reality, basically, from some point, it doesn't depend on ensemble size. So if our system behaves like that, we can see that it's much more important to have in our ensemble to pass some critical rank threshold to perform correctly, rather than have bigger and bigger size to reduce spurious covariances. However, if we use traditional NKF, it works the other way around. We can see that the spurious covariances are perhaps important at any ensemble size. So basically, the answer is that both of these factors can be important and work with different weight in different systems. So the localization in NKF is mainly empirical fix. It's done because we have no other choice. And when we are doing that, we are paying some price. What this price is? The first obvious victim is the dynamic balance in our system. For example, consider planet Earth and say some tidal wave. So, tidal wave on Earth. And for example, we simulate satellite measurement of the surface height elevation with tide being not filtered out. So this value. If we localize, what happens? We make our correction only in some area, basically around this observation, but not elsewhere. So we use the global mode. Our mode, our correction becomes local, becomes something like that. And this has nothing to do with what the actual mode looks like. So we use global modes. Of course, if we have dense observation network, we have many satellites which observe everywhere. Even if we use local framework, we can still eventually reconstruct the shape of the mode through these dense observations. But for each separate observations, we have dynamically non-balanced data. And the second victim is optimality. Which is actually related with the first one. When we use only part of our state vector, say when we apply localization, we effectively apply some nonlinear transformation for our system, and the system doesn't know about it. When we apply Kalman filter update, we this update formulas, they imply that everything is optimal, that the system is linear, and everything works right, and any change which affects this optimality, it results that our update becomes over-optimistic. Not only incorrect, like in this case, but also over-optimistic. So, and we need to take account of that. So, and note that when we make update locally, just generically speaking, when we update the mean, you can consider this as a local curve fitting. But when you update the covariance, it's nothing like that. We actually, what we are doing is that we apply Kalman filter update locally to the suboptimal system. And most probably this update has very little to do with the reality, how really the uncertainty in the system changes in these suboptimal conditions. Now, a bit of historical overview. So the covariance localization was introduced in the literature in basically in this two works. So I probably need to say first that there are two main methods of non-adaptive localization in the NKF, which can be referred to as covariance localization and local analysis. So the covariance localization, I'll describe these methods in details later. So, but covariance localization was introduced first in 2001 in two works. And local analysis was first described perhaps by Evenson in 2003 paper, and by Anderson in his 2003 paper, and by Otto in 2004. And this is approach which is used in many systems, including becoming more and more popular LTKF. So the covariance localization is a method which cannot be very easily applied to square root filters, apart from the serial square root filters like Camilla and Whittaker. And the local analysis also has its some disadvantages, and one of them is that when first described, the people only used the local window, which in some way led to the discontinuity of the analysis. We'll talk about this later. So in 2007, Hunt et al. Described a way to overcome this defect of the analysis and obtain smooth, spatially smooth analysis, despite using local analysis. And starting from 2007, there have appeared a number of adaptive localization methods, which, as far as I know, not widely used in operational systems, but maybe will be used someday. So the conventions, they are basically concerning the indexing. They're basically the same as I described in previous lectures. Now, this A small circle B is sure product of Hadamard or element-wise product of two matrices A, B, which simply means that if you have two matrices of the same size and make this sure product of these two matrices, the result is another matrix, each element of which is product of the corresponding elements of these matrices. Okay, so that's very simple. Now, A with small index I on the top means ensemble, like ensemble anomalous matrix, for example, tapered around each element, and we apply some shape function, which we just call tapering. So that's, I will use AI for this. And small f with the same index I is the actual shape function. That's fi. This shape is function which is called fi. Function which is used to taper this element. Now, this can be actually written as AI equal a sure product by some function, which is basically the taper function, but repeated in each column corresponding to each ensemble member. So this matrix consisting of the identical taper functions will be denoted as big Fi. And H, curly brackets, O, it's some another construct, which means simply the observation matrix in which the oth row, so the row which corresponds to this observation number O, isn't base, but all other elements are zero. And through these lectures, like in the end of the lectures on the skins, we will use scaled ensemble anomalies just to make the equations simpler. So just to make first introduction into this main two methods, how they work. By ensemble covariance, when people say ensemble, when people talk about covariance localization, this means that in every formula of Kalman filter expressed in terms of covariance matrix, what we do is a formal replace of the covariance with the sure product of this very covariance with some correlation matrix, which is historically denoted as rho. So this is example how it works. For example, if this is our covariance matrix, which was generated from some pseudo-real example, so this can happen in practice. And if we use this correlation matrix, the result of this multiplication, so and you can see that we imply that this is periodic domain because the correlation at these far corners is also 1. So you can consider that this is example of one-dimensional periodic domain. Then the resulting covariance matrix will look something like that. It will be much more diagonal than this original matrix. So, and this means that its rank probably will increase by bit f. So of course, if we are doing that, we use in the update not the true covariance, but this is not true anyway, but we don't use it, but we use this modified covariance. So even if we had the true covariance, then applying this operation would make the whole procedure suboptimal, because we make covariance not what it is, what it actually is. Now, the local analysis uses completely different approach. So, if in the local analysis approach, so here we modify covariance, but we virtually we use the same global analysis with this new modified covariance, and this works as localization. Now, in local analysis, the analysis is conducted in some local window around some element. For example, if this is domain which corresponds to our covariance matrix, and we consider update of some if elements at this point on the diagonal, then we can say that we calculate analysis in this point by using state vector elements only in some vicinity of this point. So what we do, so one way of doing that is to taper our ensemble anomalies, and if we taper them by this function, then effectively we calculate analysis in this very point with this covariance matrix, which smoothly goes to 0 at the boundaries. So that's the local analysis. And when we, so once again, in covariance localization, we virtually, we still do analysis in one go, while in local analysis, we do it multiple times for each element of our grid vector. Of course, if we make horizontal, say if we have three-dimensional model, and we make horizontal localization only, then we have to cycle only through horizontal grid of our model. We don't have to cycle through the vertical grid when applying local analysis. So now I will describe how this both techniques actually work. So as I said, I will start with covariance localization method. As I said, it works by replacing the actual covariance by the shear product with the correlation matrix. And why it's called correlation matrix is because it's quite important to maintain the positive definiteness of the covariance matrix in this process. So if rho is correlation matrix, then by definition it's positive definite. So, and there is a theorem that shear product of two positive definite matrices is positive definite matrix. So that's why it's called correlation matrix. So that's sufficient sort of condition to maintain positive definiteness. So take for example our Kalman game. You can see that at every place where the covariance matrix appears, we just replace it with the shear product. And we know that in Kalman filter, in ensemble Kalman filter, we don't operate with the covariance matrices explicitly. We operate with them by operating with the ensemble members, with the ensemble. So, and this same applies to this very procedure. So nobody ever, unless he has a very small system, calculates these matrices, but uses something else. Say first, if you consider this first term, then what it is and how it's calculated. say, if we have observation matrix is a very wide and not so tall matrix, and when transposed, it becomes tall and not so wide, and those rows, those columns, they correspond to different observations, and if observation is local, those columns contain 0 almost everywhere, apart from some locations which correspond to the location of observations, where it's filled with the something like interpolation coefficients. So when we multiply, for example, this matrix on the covariance matrix, on the modified covariance matrix, what we get is that it's now 0 everywhere, apart from the locations of these local observations. Okay? So as a result, this product becomes has very simple form. It contains it's of the same size as observation matrix transformed, but these columns are very close to be some specific columns of the correlation matrix. So this can be written as follows algebraically. That's the modified state error covariance matrix multiplied by HT is approximately equal by this sum. So this is ensemble anomalies matrix. Which is tapered around the location of observation, and modified by this term. So, the point is that this matrix is rather small, and this one is already contained somewhere on the disk. So we don't have to make some big storage or whatever to calculate this. Now, similarly, if you consider this matrix and what it actually amounts to, and if again we imply that the observations are rather local, then this becomes a very small observation by observation matrix, where the elements of which is just basically intersection of some bigger matrix. So we don't have to calculate this matrix explicitly ever.
The dots correspond to the observed I.
To position of observations.
Remember, you have one observation, isn't it?
Say, here we have two observations. There are two rows. This observation is made at this location. Say, this row corresponds to a state vector.
Yeah.
Right? So these observations observe this element or number of elements close to this. And the same for that one. So the main assumption used here is that the characteristic size of these observations is much smaller than the characteristic decorrelation length of your correlation matrix. In this case, you can consider this matrix as constant around this observation.
Yeah, but I thought in the localization you only use one grid point I, and then you use the localization function Fi. So you should have only one grid point.
Right. So this is for local analysis.
Yeah.
Yeah. But we are now talking about covariance localization, which is the other method when we replace the this first method when we just replace the covariance matrix with modified covariance matrix. And so, despite we're doing that, we don't have to calculate this error if our observations are local. So, in the long run, this whole, it's possible to show that this whole expression can be written in this very simple form, where this indeed are very simple, very small matrices. So, what H is the spatial mask, which is 1 at the location of observations and 0 everywhere, anywhere. So we mask this matrix rho with this sort of space mask, and then we make sure product with this guy. And actually, all these matrices are very sparse, so there are very few operations that you have to make computation to compute this. So I don't expect that it will be very hard to follow. Perhaps last time I went through it myself was about maybe a year ago when we wrote a paper which describes the two techniques. But just maybe follow the main reasoning and the main conclusions which are stated here. So, and the main point which I try to show is that computationally, to calculate all those, to apply this localization technique is not a very big burden on the system. It can be done even with a large-scale system if your ensemble matrix is very big. So to use this covariance localization technique, you must be able to represent the ensemble transformations in terms of covariance P. And this is indeed possible with NKF, because we know that the gain matrix can be expressed in terms of P. Now, this is indeed possible with the left multiplied ensemble square root filter, because again, it uses the gain matrix multiplied by ensemble. It can be used with the alternative left multiplied square root filter as well, because you can see covariance here. It can be multiplied with our GNKF, because once again it uses the gain matrix. But there is no way you can use this technique with the ETKF, because the whole transform is written what's called in ensemble space. So matrix P does never appear in this expression. So it's not possible to apply covariance localization, which relates observation space and state space with ETKF, because ETKF doesn't involve state space at all. Of course, if say historically, sometimes the sort of discontinuous matrices we used for the correlation matrix, and those matrices, for example, which are 1 everywhere and 0 elsewhere, are not positive definite. If you calculate eigenvalue decomposition of such matrix, you can see that there are a number of modes which have negative eigenvalues. And how you can see that is that this cannot be possibly a correlation matrix. Is that, for example, if some element of the state vector corresponding to some point on the diagonal is correlated with some other vector, say, with correlation coefficient close to 1, and this other element is correlated with yet other element those two faraway elements also should be correlated between each other. But you can see that the correlation is actually zero. So that's sort of inconsistency which is reflected in not in this matrix not being positive definite. Now, even if we use a well-behaved correlation matrix, but in eluded domain, where we make sort of, say, in this case, say, this is a genuine correlation matrix which is positive definite, has no negative eigenvalues. But for example, if we use it in periodic domain, and what we do in this point, we now have the matrix become non-smooth in this direction. And this non-smoothness at some location, it can still result in not being positive definite. So when you apply this technique, you should be rather careful that you maintain positive definiteness of the correlation matrix regardless of your model geometry. And so this is just an example how this matrix row looks in two-dimensional case. So this is how it looks like in MATLAB in one-dimensional case. And that's how it looks in two-dimensional case. So we now go to the local analysis. So how it works is that when, as I said, when calculating analysis for the element I of our state vector, which corresponds to this row of the ensemble matrix, we multiply each column on the ensemble matrix by the taper function. So as a result, we use much smaller ensemble. So why tapering is important? Consider that we have two-dimensional spatial domain, and calculate our local analysis in some window around some element. And we're actually interested in the analysis in this element, but we calculated it for the whole window. So the observations outside this window, they don't affect the analysis because the ensemble spread is zero. So the basically the ensemble is non-responsive to those observations. So only observations inside this window do matter. So when if we calculated our local analysis, these observations inside window, and consider that we now want to calculate analysis in the neighboring point. So we move the whole analysis window one grid point to the right. And what happens now if a new observation enters this new analysis window? This observation hasn't been assimilated for this grid point, but it will be assimilated for that grid point. This means that if there is no tapering, that our analysis becomes discontinuous in space. So to maintain spatial smoothness of the analysis, we need to modify our system in some way, in such a way that the impact observation, when it only enters the analysis window, is small. And then this can be done in two different ways. Historically, in their work of 2007 with locality F, Hunt et al. Achieved that by increasing observation error variance by a factor which goes to infinity at the local domain boundaries. So the equivalent way to do that is shown here on this slide is to taper ensemble anomalies within this domain. And why this is equivalent is shown here. That's, for example, consider Kalman game. That's the expression for the local Kalman game used for the update of ith element. Right? So this expression can be rewritten in some blocks, which I put this here in rounded brackets. So it's the same blocks, and you can see that these blocks contain the observation error covariance to the power 1 minus half by ensemble anomalies. So we can either increase the variance of observation error covariance matrix, the variance of observations, or we can reduce the magnitude of ensemble anomalies to the same effect if done correctly. So, and this last r to the minus half, it actually acts in this state update equation. It acts on the innovation vector. So, for these two methods of tapering become fully equivalent, we also, if we choose to taper ensemble anomalies, we also need to taper our innovations. So all schemes which can be expressed in terms of Kalman gain, and there are a number of them, this for all schemes we just proven this equivalence. But for the schemes which cannot be expressed in terms of Kalman gain, for example, for ETKF, this remains true as well. So here, this the ETKF ensemble transform matrix is expressed in the same blocks as the Kalman gain. So in our operational system, we actually use this second method of tapering ensemble anomalies, and this same method is used in the NKF MATLAB package. So you can look at the file which is called analyze.m and see how it actually works. So this file, analyze.m, is written in such a way that it can be easily understood. So I've tried to maintain that its simplicity, and each scheme only takes a few lines of code in there.
Excuse me, previously you mentioned that the external Kalman filter, you cannot apply the localization.
Extended?
You listed a number of types of Kalman filters, and the last one was extended.
No, it was ETKF. We can't apply covariance localization in ETKF. In this, say, for this ensemble transform matrix, we can. So the local analysis is, in some way, it's a very good method because it's scheme independent. The only thing we do is we apply analysis in the local window. Okay? So we can apply local analysis with any scheme. But to apply the previous method, covariance localization, we need to calculate virtually the Schur product of the correlation matrix and covariance matrix. And if the method, some equations of the method do not contain this covariance matrix, like this ETKF equation doesn't contain covariance matrix, it's impossible to do that. So the conclusions about these two non-adaptive localization methods. So covariance localization can only be applied to schemes formulated in the state space. Can be inconsistent depending on the taper function and also on the model geometry. It can be formulated via either covariance filtering or tapering of the ensemble anomalies. I didn't talk much about that, but if you want the details, there are in our paper on these two methods. And also, computationally, it can be the most effective choice for system of intermediate size. Say, if you have system, say, of quasi-geometric model in the nkf-MATLAB package with the state vector of size of, for example, 15,000, it's not really a large-scale system. The whole ensemble can be written into the memory and kept into the memory. So that's not large-scale system, that's intermediate system. And the gain methods can be calculated explicitly and kept in the random access memory of your computer. So in this, and if you want to run the system fast, then the best scheme perhaps is to use covariance localization, because after you calculate the Kalman gain, you can apply the update just in one go.
Your third point, if you use the tapering of the ensemble, can you apply it still to the extended Kalman?
To the TK?
Yeah.
No.
Still.
Because the tapering of the ensemble the expressions for the tapering of the ensemble, they are derived like just a second. Like here, for example, this expression is expressed by tapering of the ensemble. So that's the tapered ensemble. About this observation, about the location of this observation. And that's the same. So to be able to apply this, we still need to start with this guy. If it's not in the updated equations, it's not clear how to apply this method code. So we just replace this computation with that. So this is the tapered ensemble. This is localized covariance. But if you don't have localized covariance from the very start, say like in the ETKF scheme, it's not clear how we can apply it. Now, I've put up the experiment here. I'll prove the pass on that. So the idea was to run the same system with the nkf-MATLAB, both, and run it with exactly the same settings, the intermediate size system, run it with the same settings, but with two different localization schemes, and observe how much one scheme is faster than the other scheme. So we probably can do that at some point if we will have a bit of time in the end. But I planned to do that just to substantiate this observation. Although I have to say that the package is not specifically optimized for performance. It's mainly written for research and educational purposes. So concerning the local analysis, it can be used with any scheme. There are no restrictions. You just use local window. So the local analysis is always locally consistent, because as soon as we calculate the new covariance, the updated covariance in this local window, or as soon as we modified our observation error covariance matrix, from this point on, the update is consistent. It's not possible to get something going wrong. Like in this case, you can get, if you do something wrong, you can get non-positive definite covariance. Well, in this case, it's always consistent. This doesn't mean that it's globally consistent. Of course, it's globally inconsistent because we use this window only to update one element. Then we use different window to update adjacent element. And if you consider what we're doing in these two elements, this will be globally inconsistent in the Kalman filter framework. Now, this approach can be formulated via either tapering of ensemble anomalies or scaling of observation error variance. And computationally, for some systems, it can be relatively expensive, but it's very scalable. So if you have really large system, large scale, what we call large scale system, like in meteorology or in oceanography, it's a very attractive approach because you can, it's very parallelizable because those local analyses run in different local windows, they're completely independent. Say, in the past, it's just takes some minuscule time to calculate all those local analyses. So we use local analysis, and the calculational part takes perhaps 5% of the whole analysis part, the calculation part in local analysis, 5%. And this analysis part, in turn, is about 1% of the propagation.
So the inconsistency is basically unaffected by the choice of the kernel function, of the kernel function.
So yeah, about the taper function. Yeah. So there are a number of common choices. So the very attractive choice indeed is the Gaussian function, but the inconvenience is that it has not local support, so it's not zero everywhere. So you have to make actual calculations everywhere. So ideally, you would like to use function which is never, which generates, which have nice positive definite sort of properties, and yet goes to zero at some point. You don't have it to be particularly nice when you use local analysis, but you want this function to be very nice when you use covariance localization. So, and the common choice is the so-called Gasparian taper function. So if you make a search, you'll find this in the literature. I think it's maybe 96 or 98 work. And what it actually is, it's very close to Gaussian, and it's constructed of some polynomials, and in such a way that if, for example, you construct correlation of function with this this diagonal, with this taper function, so it's always positive definite. So that's the common choice, the Gasparian form taper polynomial, which around here it's like Gaussian, but has compact support. So, any more questions?
How do you decide the size of the window to use for the local analysis?
Yeah, that's a good question, and the right answer is by tuning. So we try different sizes. So the simplest choice is to use some uniform window size for in your system, or some uniform characteristic length in covariance localization in your system. If you don't have some specific reason to make it spatially variant. So it's not very hard to try different things, but say in the past we use spatial window of 350 kilometers, and this is the Gasparian cone function, which has distance between the support point, the support radius of 350 kilometers. But if you calculate the effective radius, this one, it's actually about more than 3 times smaller. It's about 90 kilometers. And of course, we would like to you would like to make this value as big as possible, because the larger is the localization radius, the more dynamically consistent is your data, right? So, but you also want to match the number of degrees of freedom of the physical system, which is sort of in the spatial circle of this size. We only have 100 degrees of freedom. So we make multiple experiments, starting from 600 kilometers, then 500, etc., etc. So, and by just trying and analyzing how the results look like in different regions of the world, we just finally converge in some way.
Okay.
Just no question.
Yes, sure.
Would it be convenient to go for full width half maximum in this case? What would be full width half maximum for this window?
The maximum.
To choose localized window. And you say rather to apply some different windows.
Apply different windows.
Yeah, I mean you have a good optimum window for localization.
So you mean in each spatial point you choose its own window.
No, I mean regarding this question.
Yeah.
To which optimal selection will be choice.
So you make you start from the same forecast and you make multiple analysis. Each time you use different size of your local window. And then you analyze the results and make some decision.
Okay, good. Thanks then again. And I wonder whether we will have any student presentations. You are the only one who mentioned to me something the other day. Is there anybody else who would be interested in showing and telling us? It doesn't have to be a formal presentation, it can be even just on the whiteboard. And maybe that is especially to people who are participating in the next week, so that we can learn a little bit about what their interests are. Okay, then if you have something ready, good. Okay.
Maybe it's not much related to the.
Yeah. But anyway, it helps us to get some idea of who we are. So we have one presentation. Your name is Fallah. Yes, that was it. Right, so let's see where the computer works. So you have your own computer, yeah? Right. If somebody does want to grab the food or something. There's a coffee machine here that allows you to refresh your
was ist die Männer?
Metro, yeah.
How are you leaving? Yeah, the booking is for 7 p.m. You can meet at the station there, and then you go.
Station, the place for meeting is
It's very close to the.
but I mean, are there several exits from the metro? Are there several exits?
You would probably go left, right? Somehow.
From the exit of to the left.
One exit to the left and
Yeah, it's the only exit that goes to the city, to the city. The one that to the water. Yeah.
So that's the T-bar that we need to go to, Gamla Stan.
Yes, that's it, yeah. Good.
You could have the whole thing around, just let it.
Yeah, my name is Bija, and I'm from Iran. I'm from I work at the Iranian National Research Center for Cloud Seeding, and we actually do the cloud seeding with the aircrafts, but we are going to use some ground-based generators for cloud seeding too. That's why we have to know the wind field of the region to put these generators to the optimum position. So in order to convince my boss to use the numerical modeling for finding the wind field, I have used a numerical model named WRF, Weather Research and Forecasting System, to show that these models are very handy and useful to forecast the wind fields. So I have used this model and the two-way nesting for the region. Here is Iran, and that's the first domain, and it is the second domain in it, and this is the last domain with the resolution of 2 kilometers in grid space. And I just here show the results. I actually have used 2 different initial data for initialization of the model. One of them was GFS data, Global Forecasting System, and the other was FNN data, final reanalysis data. And that's the,
what is the horizontal quantity here?
yeah, that's the vertical height. That's 900 hectopascal up to 100 hectopascal, and that's the model height.
Okay.
Height, yeah. It shows that, and the observation is also the sounding in Tehran region. It shows that the model has forecasted the height very well. And that's the temperature, forecasted temperature and the observation. Again, in 1 point, regarding to the vertical dimension.
This temperature is in what units?
Excuse me?
What are the units?
Unit of temperature, centigrade.
And so with F and L means?
FL is a data meant final analysis data. I think it's for the N card.
Okay.
Yeah. And that's the dew point. It shows that the model cannot actually predict the dew point so much.
So these are climatologies.
Climatology.
These are taken from what date, which dates?
It's a simple. It is after. Oh, excuse me, I didn't say it. It is after 48 of model forecast. I have run the model for 48 hours, and this is the result with the observation.
But when which circumstances from initial conditions which corresponded to a particular situation, from what were the initial conditions of the model?
What were the initial conditions?
From which initial conditions?
You know, the model uses, I have just, I don't play with the initial conditions or any scheme, but I have used different data for the input. You know, the model uses, for example, the GFS data. Okay, the GFS data is from a global forecasting system. GFS is also a model, but it is global. It doesn't have any boundary. You know, every 6 hours the data comes out on the site, and the data are for the next seven days. So you can download it, for example, today for seven coming days. But it is the resolution is just 1 degree, approximately 100 kilometers. But I wanted to have a better resolution, about 2 kilometers. So the model just uses this GFS data for the boundary conditions, you know, and the initial data. For example, in every 3 hours, it is the model's step. After 3 hours, the forecast is going to compare itself on the boundaries of the model with the GFS data, and it corrects itself on the boundaries. Did you get your answer? Yeah.
Is this only 1 pound of the average of your domain?
It is just one point.
One observation or
Yeah,
one
one
station?
point exactly in a station. Yeah.
But then
In an airport station.
But what about your global data is integrated into that part, or but the GFS is the global data, right?
Yeah.
It's also for nearest the grid point or interpreted to your station.
Yeah, I'm sure before. Look, it's my domain, okay? For example, this is my, this is my domain, okay? The model uses the GFS data. For example, the GFS data has 40 points in this domain, okay? And the model is going to use these data for initialization and also to correct itself every 3 hours. You know, exactly, GFS model doesn't have around the globe every grid point the amount, the quantity.
No, but I think the question is how the results from your model compare with the interpolated results from the global model.
I didn't. I compared the model output with the observation, not with the global model.
Okay, your model, if you scroll down a little bit to, so it's the 2 different simulations from different initial states. You are comparing.
FNN and GFS. There are different inputs. It's a simple one. It's not so scientific, you know. I wanted just to show that the WRF model can simply be used to show the wind field of a region, you know. Because for cloud seeding, especially for the ground-based generators, we have to know the wind field in advance. Yeah, and that's relative humidity. Of course, the model didn't resolve the and doesn't have a good forecast of relative humidity. And that's the wind direction. It is obvious that the model results of convenience, just not for the 800 hectopascal and 750 hectopascal. And I think that's the observation error, because I have run this model for another region, for another city. And in these points, also they have a correlation with the observations.
And what are the units on the y-axis there?
Wind direction. This?
Yeah.
This is wind direction.
Yeah. So, but it's round about just one complete rotation.
Yeah.
And
yeah,
two
that
rotations.
shows that it is
so maybe it's actually better than
error. Yeah. Yeah, thank you.
That's all right.
And that's the wind speed. It's also convenient that the model has forecasted the wind speed also to a good extent. And that's the errors of, it's a percentage of errors for FNL and GFS. And it shows that FNL has a better response for the forecast, because FNL data are data which are reanalyzed, and they show better results than global forecasting system.
Is that meter the units, vertical units?
Not the result percentage. For example, 1%, error is 1%. It is I think this is, for example, forecast minus observation. That's single. I've simply calculated it. It's for height, model height. But
there's a bias because the observations are always less than the forecast.
Yeah.
So we have a bias in it.
I have I think. So. Yeah. And less temperature shows much more error, especially near surface. You
didn't show this to your boss, did you?
No, I wanted to just for the wind field. I wanted to show that it has predicted wind field, here is the wind field, wind direction. The errors are less than 10%. It's convenient, it's a simple run. Maybe with a better post-processing or some stochastic methods. You have to train your model for a region, especially, for example, you have to use, every model has different schemes. For example, for cloud microphysics, WRF has 5 schemes, 5 different schemes. One scheme has a better answer in a specific region, and this scheme has, for example, a dramatical answer in another region. You have to use them with a trial and error algorithm to know which setup is better for your region. And that could be an ensemble method with different schemes. You can have an ensemble of I don't know, maybe 100 models, 100 different models with 100 different setups. Maybe a setup one setup on a specific setup can forecast rain, precipitation better than the other setup. It's a large work, I think, to do. Train a model for a specific region. And I have another. Show. It's a comparison of actual maps with model output. It's the actual map of and it's the date. It is actual map of Iran, and that's my model's output. It shows correlation between these two. For example, this contour LN68 goes near the Caspian Sea, and here it is LN68. So it is similar. And different levels. That's 500 hectopascal. You see, it has predicted.
When you say actual map, it must be an analysis produced by center, which center?
The actual map is from the Iranian meteorological center. Yeah. I think it's the objective analysis of the stations. You can see it in the sites too. They upload it every day. Yeah, the model has predicted this low, exactly at the same location. And that's the total precipitation of the model forecasted, and this is NCEP NOAA reanalysis data of the day. You see, for example, this maximum is forecasted by the model, the location value, but the amount of it is has a dramatical error. This maximum is nearly 8 millimeter, but in my model it is near 20 millimeters. It shows that the model has just localized the maximum, but not the amount of precipitation. I think that was my presentation.
Very good. Thank you very much for telling us about your work and interest. And are there questions for that? Please.
What did your boss say?
Is that, yeah, he agreed with me. Because, you know, in Iran we have lack of data. And, for example, I have done a work, I have done a project, and I have collected data, and I suddenly have noticed that my data are shifted one day. And I went to the person who was responsible of this, and I asked what has happened. He said, "Oh, I haven't considered the leap year. Before year." I told, don't tell anyone. Okay, okay. So these problems we have in our country, you know, and we have to find the alternative ways. And the models are very handy and easy to use, you know. And the initial data are also available.
Yes, please.
How many weather stations do you have in your country?
I don't know.
Automatic weather station.
I don't know.
Okay, yes.
But I can
You know,
say
you
I can
can
say you tomorrow.
Assimilate this information.
I can tell you tomorrow.
Yes. Thank you.
I have a question.
Yeah,
I
okay.
want to know your initial data for the forecasting. Where does it include the observational data?
Initial data.
Yeah.
You want to know?
Initial condition for the casting.
Yeah.
And does it include the observational data information?
You want to know what is the initial data that I have implemented in the model?
Yeah.
Yeah, I have told it was two sets of data. One was GFS and another was FNL. I didn't put any data, for example, station data. I have just used these data. They are in grid 2 format, and you can see them easily. I haven't used assimilation.
And what's the resolution for your forecasting? What's the resolution?
Other resolution?
Yeah.
I didn't get your answer. Any question?
The resolution, you said, yeah?
Yeah.
Resolution.
Yeah.
What was the resolution?
Yeah.
I have used the nesting. You know what is nesting? Yeah. The first domain. The first domain was 18 kilometer, and the second domain was 6 kilometer, and the last domain was 2 kilometers.
How many stations, observational stations in each period?
I haven't used observation data for my
So
model.
you compare
I've compared it just in the middle of the domain here.
Yeah.
Just one observation, and that was the sounding of this point.
And the
Just
observational
one sound.
data is included in the grid. The observational data.
I have just compared the output of the model with this point in vertical.
Just this point.
Yeah, it's just this one. And that has error too, because these balloons sounding, they go just with the wind field. They don't go up straightly. You know? Maybe the I don't know. Maybe the temperature here is different from here, and you know.
Okay. There are no further questions, and let's thank him again. And, if anybody has made up their mind and wants to present anything on short notice, no? And there could be still a chance tomorrow, of course. But I think that's it then for now. And if people want to sit here, they are welcome to stay here. Anywhere here in the lecture room or also in the building, of course, work or talk to other people here. Any questions?